Hello YouTube, I am Arend and today we're going to be talking about how to do Minecraft style random terrain generation in Unity. So we're going to be doing this using 2D Perlin Noise. I'm looking forward to it. It should be a lot of fun. So let's go ahead and do some Minecraft terrain generation.
Alright then, let's get started. So to start off with, I'm going to give you a little teaser. I'm going to go ahead and show you the final product of what we're making today. As you can see, it looks like what you expect for Minecraft terrain. Looks fairly random, and we got some natural-ish looking hills and stuff. Alright, so to start off with, we're going to actually start out with our Terraria program from my previous tutorial. If you haven't seen that yet, I would recommend following that first, and you can find a link in the description to the Unity Terraria tutorial. Alright, here we are. If I hit play, you'll see that it's the Unity Terraria tutorial. So every time I play, it generates new terrain. Okay, so first thing we're going to do is we're going to convert this over from 2D to 3D. So we're going to need to change up our prefabs from being these sprites to actually being some cube things. So what I'm going to do is I'm going to create an empty game object, and we're going to name it, let's name it grass, I suppose. And I'm going to, within that, I'm going to create a plane, and then I'm going to create actually 6 planes, so I'm going to hit Control D on there a few times to get 6 of them. And I'm going to name them top, and next one's going to be bottom. So this is just going to represent the 6, before I duplicate them, let me set up our top. Okay, let's just jump in there. I want it to be 3D, so I'm going to uncheck 2D, and there we go. Got a 3D plane there. Alright, so I'm going to scale it down to 0.1. Its dimensions are currently 1 in Unity units, but for whatever reason the default dimensions for the plane is 10 by 10, so I'm scaling down 10 by 10 by 0.1 to make it correspond to 1 unit in Unity dimensions. Alright, so now we're going to duplicate this a few times, and we're going to rename these all accordingly. So we got top, we got bot, we have left, we have right, we have front, and back. By the way, if you're wondering how I'm able to rename these this way, it's F2. It's a handy trick. Okay, so right now they're all in the center. I'm going to move top upwards, put it on top, so move it upwards by 0.5. I'm going to move bottom downwards by 0.5. Rather negative 0.5. Okay, and there's this thing about the way planes work in Unity and graphics in general, is that from here it looks fine, but from down here I can't see it, which kind of makes sense because usually polygons are only seen from one side. So to fix that, since this bottom one is going to be seen from the bottom, I'm going to actually rotate it along its, I suppose, z-axis by 180 degrees. So you see I cannot see from the top, but I can see from the bottom, which is what we want. And also a little miscellaneous thing, all of them are the same color. I'm going to add it's hard to differentiate them, so I'm going to go and add a light source. So if I go light, directional light, add you up here, and that should look much better. Well, I guess let me rotate the light source a little bit. Yeah, there we go. Okay, that looks better. Alright, so we got top, bot, now left. Left's going to be negative 0.5 along the x-axis, so I guess I should be looking at it like that, yeah. And we're going to rotate it as well. Let's see, so we want to rotate around this blue axis, which is z, so that'll be 9 degrees. Here we go, I can see it from there, perfect. Right, going to move it by 0.5, going to rotate it along the z-axis, which actually by 270, so that way I can see it from over here. I'm going to try and go through these a little quicker. Z, I'm going to do negative 0.5 for front, and rotate along the red axis, which is x, so 90 degrees? No, 270. Yeah, I got to be careful to have the right one so I can see it correctly. We're starting to get a good looking cube, just one more. The back one needs to be shifted by 0.5 along the z direction, and we're going to rotate it by 90 along the x-axis. Alright, perfect. So we got a cube. We've got a cube. Now we want to color each side. So this is going to be grass, so I'm going to color it according to our grass things. So let's see, the bottom is going to just be dirt. Hard to see, but trust me, it's there. The sides are all going to be this transition. Doesn't look very good now. I'll fix that later. And then for the top, we actually need a new one. So I'm going to go ahead and I made something in Paint.net. Just click Gradient, and I'm going to drag it in from my desktop. There we go. And of course, there's a link in the description. So if you want to use the exact art that I did, you can just download the link to the source code, and then you can go ahead and use the same graphics that I'm using. Alright, so to fix these guys, I'm going to rotate them. So let's see, this left side, let me see if I can figure this out. So this green one is only going to rotate it by, green it corresponds to Y, so that's 90 degrees along the Y axis? No. Nope. Okay. I had some trouble with this when I was initially in the tutorial, so I ended up a lot of times resetting it down, and now I can rotate it along the Y. No, not like that. 270, and then rotate back up. Nope. Now I have to rotate it along the X, maybe. There we go. All right, I'm good. I'm gonna have to fiddle with each one. That one really looks good. This one, I reset the Z. Got to rotate it along the Y. Now I got to rotate it along the X. Okay, looks good. U. Maybe set that. Rotate it by 180 around the Y. So the reason why I keep resetting it is because it looks like Unity rotates along the Y first. So I should apply the rotations in the order that Unity applies them. So that's why I'm doing it this way, because rotations can get tricky. Alright, there you go. We got a pretty good looking cube there. Awesome. So now I'm just going to go and drag this down here, and I want to override the previous prefab. So it used to be a sprite, but now when I replace the prefab is now a cube. Okay, so we're going to do a similar thing with dirt. I'm going to hit Control D on there to make a new grass, and then I'm going to use F2 to rename it, and we're going to call this one dirt. This one should be fairly easy. I'm just going to go ahead and drag in the dirt color on top of all of them. But first, of course, I got to drag that away so I can see them. If they're on the same place, I have trouble seeing them. And drag dirt onto all of them. And very cool. Now I'll drag this down here and override the prefab. Awesome. Alright, so now some minor things. Our camera, let's make it, right now it's orthographic projection. We want to be in perspective projection, which will make it 3D-ish rather than the 2D. There's more to it than that, but that's the main difference. Now I hit play. You can see it's already looking pretty good. It's already taking our Unity terrain our Terraria terrain, and it's actually looking pretty good. So I'm going to jump into my scene, and if we take our camera, we can see that's what it sees right now. But we want to look a little better than that. So let me see. I'm just going to fiddle with this a little bit, get it to look just right. Maybe I'll rotate it some, 45 along the Y, 45 degrees along the Y. We'll try that for now. I'm going to rotate 30 along the X to make it a little bit downward so we can see the top some more. I'll probably want to adjust it more later, but that's good for now. So for those of you who are new to Unity, the way Unity works is, right now I'm in play mode. So when I unhit play, it's going to reset all the stuff I did to the camera. So in order to avoid that all resetting, I'm going to go ahead and right click on the transform. I'm going to hit copy component. Then I'm going to unclick play. You see it resets. That's okay because I just copied the values. So I can right click on the transform and I can hit paste component values. Now I hit play. See, it looks pretty good. Alright, so this is their Terraria terrain now rendered in 3D using our new cubes. Yeah, so you can kind of get an idea for how we're going to proceed from here. So we've got it along one dimension, and then we need to add stuff along the sides to make it more like a Minecraft style terrain. Okie doke, let's jump into it. So we're going to start off in our generator, opening up in my old faithful text editor, Notepad++, still going strong. Alright, so our generator is going to need to work a little bit differently. So right now we've established bounds along our X and Y direction. So let's add some bounds along the Z as well. So I guess do -16, and max Z is going to be equal to 16. Alright, very cool. This looks good, okay. I'm going to need to mess or regenerate a little bit. We've got width and height. I'm going to copy that and go ahead and add depth. So this is going to be equal to the velocity scale along the z direction. All right, we got depth. We're going to need another loop in here. So for k, we'll say k equals min z, k less than max z, k plus plus. All right. Got another loop. So now we have these nested loops. So each iteration in here is going to represent one, I guess, column in our grid, and it changes from just a line to a grid by adding this next loop. And this, our I is going to represent our current x position, k is going to represent our current z position. All right. So now for the column height, we're going to need to take an extra parameter. So right now it's taking in which x, and then the range or the height, maximum height, and we're gonna go ahead and add in our z, so it'll be k minus min z. I think I'm just gonna enter here and move to the next line. Alright, it's looking good. So we're gonna need to do some work in here to get that working, but before that, let's see, we need one more thing, I believe, in here. Okay, right. When we're instantiating it, we want to instantiate it to a place in 3D space, not 2D space. So a vector 2 just isn't going to cut it anymore. So we're going to need a vector 3, and it's going to be the same x, same y, but we need to add a z term to it. So I'm going to just enter again. What am I doing? Enter, and tab. I'm going to add a z term to it over here, and it's going to be k times depth. Alright, looking pretty good. So that should make a fair bit of sense. Now what we got to do is modify this get noise. So if I hop back into Unity, that is actually in our Perlin noise. You can see right here it telling us that get noise isn't ready yet, which it's not. So I'm going to open up Perlin noise, and now we're going to mess with our get noise. So we got to change it to where it's going to take an x and a y. So int x and y. Alright, chunk size good, noise is good, range okay. Alright, now we're getting into the core of the algorithm. We're about, let's see, 13 minutes and probably a little bit less. Or probably about 13 minutes, roughly, according to my estimate. And this is basically what you came here for. This is how we generalize the algorithm to work for dimensions instead of one dimension. So to explain this, I'm going to pull up my little, my slides that I made for you guys. And hopefully, after going through those slides, it'll make sense. Alright, so allow me to establish our baseline. This is how it worked in the Terraria, that is. So this is our starting point. So for any point, we're basically trying to find a value between two random numbers. So we've identified a random number to our left, which is I'm going to call R0 to simplify a little bit. We got a value to our right, which I'm going to call R1, so to simplify a little bit. For as far as how this relates to our code, you see we have left random here. That's going to be the R0. And we got the right random here, which corresponds to our R1. And so we have those two values, and then we need to find a point in between. Okay? So our point in between is going to be determined based on how far in between. So if we're closer to R1, we want our value to be close to R1. If we're closer to R0, we want our value to be closer to R0. And that how far we are is determined by this variable t, which we actually called prog over here. But I'm going to call it t. So we call it prog over here, but I'm going to call it t in here to simplify the variable. Alright, so far so good. Okay, so now how do we compute this value over here between R0 and R1? We used linear interpolation, which is basically this algorithm. So R underscore 0 times 1 minus t, which makes sense because if t is 0, we're right on top of R0, and that therefore this will be R0 times 1, give us R0. And then we're adding to that, we have R1 times t, which makes sense because if t is all in the right side, really close to R1, t will be equal to 1. This will just be R1. So this is linear interpolation, and this is how we determine this value in question over here. Awesome. Now that we've got that down, let's talk about how we can generalize this to 2 dimensions instead of 1 dimension. Okay, so for the 2-dimensional case, instead of looking like this, it looks more like this. So we still got a random point somewhere we need to figure out, but now instead of just having a value to the left and a value to the right, we need to figure out our value based off the values in the corners of this square. So we've got R00 representing the top left corner, R10 representing the top right corner, etc. And then we have two progression variables. We can represent our point as some proportion of the way between along the x-axis from left to right, and we can use this ty as some proportional way between along the y-axis from top to bottom. So for my variable names here, I'm letting the numbers indicate which corner. So the first number is value along the x. So you see values along the right are all 1, values along the left are all 0 for as far as the x value. And the right one represents the value along the y. So along the top they're both 0, and along the bottom they're both 1. Okay, so now let's talk about how do we break this down. So to start off with, we're going to compute our R0 and our R1 as values in between the top and the bottom. Okay, so to do this we can just use two linear interpolation algorithms. So I'm going to pull it up here. So R0 is just a value between R00 and R01 as shown here, and it varies by t underscore y. So we're using t underscore y to show how much we vary in between. Okay, and we do the same thing with R1. We compute that as a value between R10 and R11, R10, R11, and it also varies by t underscore y. Now this might look familiar to you. We have variable R0, we have a variable R1, and we have a random point between which varies by some proportion along the x-axis, right? So now we've basically simplified the problem down to this. So it looks like that, all right? We've simplified the problem down to this, which, if you remember correctly, is exactly the same as our original one-dimensional problem. So the way I like to put it is we've squashed down the y dimension, and we're able to focus purely on the x dimension because we've got these two values that are values along the y-axis, and now it's just an x progression between them. So now there's one more linear interpolation between them, and we can find our final random value. Alrighty, so now that we've got the theory of our algorithm down, let's go ahead and implement the code, shall we? Okay, so this chunk index, I'm going to rename it to index x. So this is which index along the x-axis. I'm going to copy that, and then I'm going to call that y, I'm going to call that y. So now we got an index along the x-axis and an index along the y-axis. Works exactly the same way. Alright, so now this prog variable, we're going to change that to t underscore x. This is a progression along the x-axis. I'm going to copy that, and I'm going to replace the y's just like the last time. So now we've got our progress along the x and our progress along the y. Alright, fairly simple. We're still good. Now for this left random, right random, basically based off of the nomenclature we're using in the little theory section, this would represent R00 and this would represent R10. So top along left side and top on the right side. Okay, so we're going to copy and paste both of these to make their y equivalents. So this one is top, this one's going to be bottom, this one's top, this one's bottom. There we go. We have our 4 variables, and let's see. I'm going to need to rename this. All of our chunk indexes are going to need named to chunk index or index x. Let me do that real quick. All right. So now for this random function, it needs to take in an extra parameter in order to make it different based off of the y indexes as well as the x index. So I'm going to pass an index y as another parameter. I'm going to do that for all of them. Alright. And I'm going to do some tabbing to make them line up nicely. Alright, so notice with our convention here, 0 is along the x, so these ones are plus 0. I can probably write that out, plus 0. And then these ones are plus 1 along the x, and then we can do the same thing along the y. So this one's plus 0, this one's going to be plus 1, that one's going to be plus 0, and that one's going to be plus 1. Beautiful. This is looking good so far. Now, of course, we've got to change our random to take an extra parameter. I'm actually going to write a new one. So private int random, and we're going to say long x, long y, and int range. Alright, so basically what we're going to do is we're going to return random something comma range. And for this section, we're just going to find a way to combine x and y. Now, conveniently I do that, we just x plus y. But the problem with this technique is that we end up with some unintentional. We just end up with some symmetry that we don't like. So, if the x is 1 and y is 2, it will be the same as if x is 2 and y is 1. See that? So if we flip the numbers, it'll come out the same, and we don't want that. We'll end up with a symmetry. Okay. So to fix that, I'm going to multiply one of them by some big number, 65536. I see people use that number, or something similar to that. Maybe it's 6535. I see people use that number a lot. There's probably something special about it. I don't know. But yeah, just a big number should work. So that's how that's going to work. So now that we've got our corners, we want to compute our R0 and R1. So we got R0 is going to be equal to lerp. Let me think. So we pretty much want to do this whole equation again, but it's kind of messy to copy and paste that over and over again. So I'm going to actually make a new function called lerp. So to do that, it's going to be float. Let's see, I guess it'll be private float lerp, and we'll do it from some left value to some right value. Let's see, those should be floats actually. So float left, float right, and then we're going to do float t to represent the progression between those two numbers. And then we're going to return, let me see, it'll be left times 1 minus t plus right times t. There we go. That's our linear interpolation algorithm. So for R0, we lerp from R00 to R01, and we vary it by t sub y, because we're squashing down the y-axis. And this is 1, that's 1, and that's 1. Okay. So now we've got our two variables along the x-axis. We've squashed away the y-axis. We no longer have to worry about this y progression, and then we can compute our final, I'll call it final r value is going to be a linear interpolation between R0 and R1, and it's going to vary along tx. Okay, and now we can basically just add r to this noise, and I think that does it. That's basically all it takes. So not too bad. There's 26-minute tutorial or so. Well, yeah, we're about 26 minutes in. Pretty good. Okay, but of course we got some errors. Would be surprising if we managed to make it to the whole thing without an error. Okay, so I forgot a semicolon. What else? It's a vector cannot be found. Are you missing? What are you talking about? 37. What's happening on 37? Okay, I said vector 3. I remember specifically saying vector 3, but apparently I didn't type it. Okay. Is there anything else that you're complaining about? No, not does it. Alright, I'm gonna save. I'm gonna play, and let's hope this looks pretty good. That does look good. I'm happy with that. Yeah, so there you go. That's how we generate Minecraft style terrain in Unity. So before we finish this tutorial, I'm going to go ahead and make some adjustments and tell you some more things you might be interested in. Let's see, so I'm going to start by just modifying the camera a little bit. There's so many things in here, it's moving kind of slowly. Let me see. Come on. Yeah, I'm going to probably cut to the camera looking the way I want it to. Alright, brilliant. The camera looks right. So I'm going to go ahead and copy this component. I'm going to hit play. And I'm going to paste the component values. Okay, now for the things I want to talk about. So I hit play. Maybe it was that 3, 4, about 5 seconds or so. It pops up. That's I guess about how long it takes to, when you first started Minecraft World, I guess it's about how long it takes to generate the terrain in the first place. But of course we have a lot less, which kind of gives you some appreciation for how difficult it is. It gives you some appreciation for how difficult it is to optimize this sort of thing. And we're going to try and scale it up a little bit to see what happens. So we're going to make it, our bounds are going to make twice as big. So let's see, our max x is going to be 48, and our max z is going to be 48. So it's going to make each side twice as big, meaning we're generating about 4 times as many blocks. So if I hit play there, expect to take like 20 seconds, something like that. So you see our algorithm doesn't scale very well. And there we go. But it looks cool, right? Looks pretty cool. But it takes longer. So yeah, we did enough to get it to look good, but we did a lot of inefficient things. Like one of them being that our cubes are 6 planes, and it's also rendering each of these 6 planes. So if you think about it, there's like thousands and thousands of planes that we're generating right now. So that's one thing we're doing differently. We're also generating all at once. So if you notice, Minecraft when you first start up, it's slow in the beginning. So it's still generating stuff when you're in the world, and that's because it's spreading it out across multiple game loops. Whereas now we're doing it all at once, so it just freezes in the beginning, which is not ideal. So yeah, that's some of the stuff that we did. Yeah, in the screenshot actually took a really long time to render that out. And in order to make it not feel like the game was frozen and crashed Unity, I actually had it create the blocks over the course of multiple frames. Okay, now the other thing I'd like to show you, just to get more of the, I probably should have done this first, just to get a better idea of how the linear interpolation looks, I'm going to, let me think what I'm going to do. Okay, I'm going to change our bounds along the wall. I'm going to make it look a lot higher. Okay, so make it 30. I'm going to decrease these bounds again. 16, 16. Jump over to the Perlin Noise. Let's see, our chunk size is 16. Change our chunk size to 8, so that way we... Actually, no, 16 is good. Okay. So if I go ahead and comment this loop out, we'll just be going through one iteration. And let's think how many sample points will there be. There should be 3 sample points along each axis because the range along each axis is 32. Our sample size is 16, so you'll end up with 1 on the edge, 1 in the center, 1 on the other edge, corner. Okay. And then over the whole grid there'll be 9 sample points. So let's see if we can see those sample points when we run it. Okay, I probably should have unplayed it first. Let me do that. Alright, let me play it again. So this one you can see the various sample points fairly clearly. Let me see if I can get it to a different angle. Okay, so you see there's a sample point up here, a sample point down there, and it's basically trying to make a plane, or do the best it can to make a plane between these 4 points right here. So you get this very smooth slope between them. And same over here, we have 1, 2, 3, 4 sample points, and it's trying to make a plane in between them. So this is what each layer of the Perlin Noise algorithm is doing. And then of course by having our loop in there and adding smaller details to it, it makes it look natural. Okay, so I believe that's everything I wanted to talk about. Thank you so much for watching. If you put this to use in one of your games, I'm always interested to see what you guys do with it. So go ahead and leave a comment or post a video showing me how you use this. I'm always curious and interested to see that kind of thing. I hope you enjoyed the tutorial and thought Perlin Noise was interesting. I haven't quite lost the Perlin Noise bug yet. I still think Perlin Noise is really cool, so I'm going to be continuing to make some more stuff about Perlin Noise. Today we went over to 2 dimensions, but hey, do you want to learn how to go over to 3 dimensions or more dimensions than that? Do you want to learn how to make fractal terrain? Do you want to learn how to make animated Swiss cheese with Perlin Noise? These are all fun things that I'm going to be making at some point. At this point, if you're watching now and I haven't released anything new, I've already made a top-down terrain tutorial, which is very similar to this one, but that's in Game Maker, so you can learn how to use 2D Perlin Noise to do top-down terrain. So it's also pretty cool. Anyway, that's all for me today. Thank you so much for watching, and I look forward to seeing you next time.